Good morning, everyone, and I am so glad and thrilled to have you here with us today to a very special IBM Qiskit Live Quantum Seminar Series. Now, in just a minute, I'll be thrilled to roll out this week's seminar with Alexey Gorshkov, and I'm so glad that you have joined us on time. We like to give everyone about a minute or two to tune into the live stream. We usually like to start with the question, where are you guys tuning in from today? However, today I have another question for you, which is, what is your favorite lecture notes or textbook or website for learning quantum computing? Now, you can share the response to that in the comment chat box here on YouTube, which is either located above, below, to the right, or the left on your screen. And it's the same place where you can ask questions live of Alexey and myself during the seminar. We like to have a very interactive live discussion, so don't hesitate at all to ask questions, answer each other's questions, and just discuss things as we go along. Today's a bit special as well, and I want to congratulate all of the Qiskit Global Summer School students who are in my lecture this morning, here with us now, and in the rest of my lectures today on Introduction to Quantum Noise. You guys are real troopers, and to everyone else who's been part of the Qiskit Global Summer School, which is currently underway, and I don't know how many thousands of folks we have, but I'm very excited for that. And I can already see some responses coming here in the chat. So folks, I think with that, it's time that we get to it. This seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. You can always go back and catch up on anything you missed and stay subscribed, but we can only ask questions here and now live during the seminar. I'm your host, Zlatko Minev from IBM Quantum Research, and now I have the pleasure and privilege of hosting Alexey Gorshkov from the NIST Gettysburg and University of Maryland, who will speak about candidate for passively protected quantum memory in 2 dimensions, and I hope I got the title right here. Alexey Gorshka, received his AB and PhD degrees from Harvard in 2004 and 2010, respectively. In 2013, after 3 years as a DuBridge postdoctoral scholar at Caltech, Alexey became a staff physicist at NIST. At the same time, Alexey started his own research group at the University of Maryland, where he is a fellow of the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science. Alexey is also the recipient of many awards, including the Fleming, the APS Fellowship, the PCASE, IUAP, and there's too many to name, so I'll just leave it there. Alexey's a great guy, as you know. And with that, it's my absolute pleasure to welcome you, Alexey, to the IBM Qiskit seminar.
Hello? Cool. Well, thank you so much. Yeah, can you hear me?
Yes.
Perfect. Yeah, thanks for the invitation and for the very kind introduction. Should I just go for it? Yeah.
Yes, maybe just tell us where you're tuning in from, and then we'll.
Yeah, so I'm tuning in from Maryland, and I'm at home right now. So yeah. Should we start? Let's see. Should we start? I can't see you, so if you're nodding, then are you there, Zlatko?
It looks like his computer froze. So yeah, let's go ahead and just we can get going.
Oh, his computer froze. Oh,
yeah,
not froze. Mine. Okay.
All right, so great. Take it away.
Okay, perfect. Yeah. So thanks again to Zlatko for the invitation and the introduction, and thanks to everybody else for coming. So we'll talk today about this candidate for passively protected quantum memory in 2 dimensions. And please, ask questions. The more questions there are, the better. And Zlatko will sort of interrupt me and ask them, or whatever the process is. So the more interruptions there are, the better. So I'm going to start with sort of a simplified 5-minute summary, so that everybody can get an idea of what this talk is about, and then I will go into details. But if you just want to get the big picture, it will be in these first 5 minutes of very simplified slides. So a single atom obeys the laws of quantum mechanics and can be either here, which we can call 0, or here, which we can call 1, or in both places at the same time. Such quantum superpositions, which can be written like this, as a C0 plus a C00 plus C11, where C0 and C1 are complex coefficients, they can store a quantum bit of information or a qubit. And thanks to this superposition principle, you can imagine that quantum computers might be able to solve many problems at the same time in some sense. And as a result, they can be much faster than classical computers with lots of exciting applications, including in materials design, drug discovery, and other applications. So the state of the art is that quantum computers already do things that classical computers cannot do, but arguably not yet anything very useful. And the challenge here is that quantum effects are fragile. And in particular, undesired interaction with the environment and also imperfect control of qubits lead to errors. And these errors accumulate and eventually ruin your computation. So the solution, of course, to this is error correction. So let me briefly introduce error correction. So how does error correction work for a single classical bit of information? So we use redundancy. We encode one logical bit and many physical bits, such as, for example, in this distance 3 repetition code. So distance means that you need to flip 3 of these physical bits to get from one logical bit 0 to one logical to the logical bit 1. So this code protects against one bit flip error. So in particular, you just keep checking if all 3 bits are the same, and if this is not the case, you just do a majority vote to correct the error. So error correction works in the same way, in a very similar way for a qubit. You again use redundancy. You encode one logical qubit into many physical qubits, and then you can keep checking for errors and correcting. The main difference, perhaps, is that in quantum, there are now 2 types of error. There's the bit flip, which is familiar from the classical example, where a 0 and 1 flip. But there's also phase flip, where the sign of the superposition can flip. And so the question that we would like to discuss in this talk is, can we avoid constantly checking for errors and correcting? And so the answer turns out to be yes. So let's first discuss how a passively protected classical bit works. So let's arrange physical bits in a 2-dimensional lattice, an n by n lattice. And let's encode the logical 0 in an array of physical zeros, so the logical 1 in an array of physical 1s. And then on each bond of this 2D lattice, let's engineer an interaction that favors bit alignment, that is 0, 0 or 1, 1. Such that the energy of a total configuration is the number of misaligned bonds. So then these 2 logical states are the only states that have a 0 energy because all the bonds are aligned, while any errors cost energy. So let's start with the logical 0 state and start flipping bits to try to get to the logical 1 state. So perhaps we can start here. Now we broke 2 bonds, now we broke 3 bonds, 4 bonds, etc. And you see that basically, as we try to get from the logical 0 to logical 1, we need to flip. We need to make more and more bonds unhappy. And indeed, to go between this logical 0 and logical 1, we must necessarily go through a state that has a prohibitively large energy, scaling, at least as n. So this means that for large n, and in the presence of cooling, we can get a passively protected classical bit. So now, suppose we want to get a passively protected quantum bit. So to get a passively protected quantum bit, we need to correct both bit flip and phase flip errors. And then there is a sense in which you can use this 2-dimensional lattice from the previous slide. You can use it for each type of error. And the result is that you can get a passively protected logical qubit that is encoded in a 4-dimensional lattice of physical qubits. So for the experts, that's the 4D Tori code. But the point is that it's a 4-dimensional lattice, but we live in 3 spatial dimensions. So what can we do? So the solution is instead to use quantum oscillators instead of qubits as building blocks. So consider, for example, an ion trapped in a parabolic potential, or equivalently a single photonic mode that's also described by an oscillator. And then let's encode the logical 0 and logical 1 in these 2 states that are 180 degrees out of phase. And it turns out, as I will explain later in the talk in detail, like in the 2D lattice, you can design the system to favor these two states and penalize any deviations. And furthermore, you can design the system in such a way that the larger the chosen amplitude is, the harder it is for noise to flip between the logical 0 and the logical 1. And now putting these things together, again, to get a passively protected qubit, you need to correct both bit flips and phase flips. And so we use a two-dimensional lattice to protect against one type of error. And then instead of using the same two-dimensional lattice to protect against the other type of error, we use the oscillator idea from the previous slide to protect against the other type of error. And so the result is this two-dimensional lattice of interacting oscillators that encodes one passively protected logical qubit. And this is what the rest of the talk will be about, but this is the main idea. So you could ask questions now, but this was on purpose supposed to be not detailed, so all the details are coming later. But maybe people have questions anyway. Am I still connected?
You are, Alexey. Thank you.
Excellent,
In fact,
excellent.
I was disconnected actually.
I know. I heard.
Our internet went down
That's
on
great.
this, and my internet went down here in the office. So. Thank you very much. And folks, this is a great time to post questions in the chat and let Alexey and myself know what questions you might already have so far. And we can go, I can bring these up to Alexey as we go along on this. So feel free to put those in the chat. And for now, Alexey, I'll just let you continue.
Good. Yeah. So this was just an overview. There should be a lot of questions right now, and I'll hopefully address them, as we go along. And please interrupt me. Right. So the outline for the rest of the talk, which we'll now get into more details, is I will review kind of the regular active error correction. Then I will describe in more detail this passive error correction. Then I will describe in detail this sort of this oscillator code, which I also call a photonic cat code. And I'll describe how symmetry breaking is related to passive error correction. Then I will again discuss in more detail this 2D Ising model that I already described in passing. And finally, I'll put them together into this photonic-Ising model in 2D. And then I will conclude with an outlook. So let's start with active quantum error correction. And I essentially already explained all of this, but I will just repeat. So undesired interaction with environment and imperfect control of qubits lead to errors. And if left uncorrected, errors accumulate and destroy sufficiently along a large computation. So the way active error correction works is you redundantly encode logical information, make measurements to identify errors, and then use coherent feedback to fix those errors. And then for in quantum, there are these two types of errors: bit flips and phase flips. So let's explain now how error correction works against a single bit flip error, just to give you a sense on a very simple example. So suppose this is your quantum information in this qubit, and then we use these extra qubits for redundancy. So these controlled knots encode our single qubit into 3 physical qubits. And now we suppose that we have single qubit errors, and let's suppose they're only bit flip errors. And let's suppose that these errors are sufficiently unlikely that at most one of them takes place. So let's suppose that, for example, the bit flip error occurred in the second qubit. So then this 0 flipped into a 1, and this 1 flipped into a 0. And now we want to fix this error. So we again apply controlled NOT gates. So they flip these two states 0, 1 into 1, 0. So we get this state. Now we can factor out again qubits 1, 2, and 3 into a product state. And then finally, if the results of both measurements of qubits 2 and 3 in the computational basis are both 1, then we flip the first qubit. Now here, only one of them is 1, so we don't flip the first qubit, and we've recovered our stored information. Good. If we had an error on the third qubit, it would be identical because qubits 2 and 3 are interchangeable. But what happens if the error occurs on the first qubit? So suppose the first qubit flips here from 0 to 1 and here from 1 to 0. So now when we do these controlled NOT operations, these two zeros flip into 1s. So you get this state, and then when you factor it out, we actually have now an error. we have a bit flip error on the first qubit. But now this is where these measurements are important. So you see that both results are 1. And when both results are 1, we flip this first qubit. And this indeed now recovers the original state. So this is just how bit flip errors can be corrected with 3 qubits. Now, certain codes, they have a threshold. For example, the surface code, which I will not describe in detail, they have a threshold. So what this means is that this code is actually a family of codes defined in an n by n lattice, where n can be increased. And then we imagine starting with a state that's in the code space, then applying some errors that we can think of as a product of local errors, each with probability p. And then we do some non-local recovery. So when I say that the code has a threshold, I mean that if this probability p is smaller than some critical probability pc, then as n becomes larger and larger, this final density matrix approaches the initial density matrix exponentially quickly in n. So basically, no errors really occur in this decoded state. Now, the problem with this active error correction is that you need to constantly do this recovery. So, error occurs, then you do recovery, more errors, more recovery, more errors, more recovery, and it can be difficult to do. So before I introduce passive error correction, I should mention, this recent, somewhat famous experiment where repeated error correction was done in a distance 3 surface code in ETH Zurich. So they encoded a single logical qubit using 7 physical qubits, where 9 of them, these guys in red, were used as data, and the remaining 8 physical qubits were used to measure error syndromes. And I won't really discuss the results or the experiment in detail. And I'll just say that this is what the actual device looks like. So this is rotated relative to this by 45 degrees. So x1 that is here and now is now here. And all of these lines, I used to prepare, control, and measure those qubits. So a pretty complicated experiment, but very exciting. So we're really moving in the direction of workable quantum error correction. Okay, so we now, on the other hand, want to do passive quantum error correction. So what does that mean? So we encode a qubit in our logical state 0 and 1. So this is the pure state psi, and then we write the corresponding density matrix. So then the full Hilbert space will consist of our logical sort of code space 0 and 1, and lots of other states, 2, 3, etc. And then we would like to couple our quantum memory to a Markovian bath, where the density matrix evolves under this Liouvillean, which is composed of a coherent evolution under Hamiltonian H, and also Lindblad jump operators Lj. Now we assume that this Liouvillean is made up of 2 parts. One part is a recovery generator that stabilizes the code space. So if we're starting in the code space, then nothing will happen to it under this recovery generator evolution. On the other hand, we also assume we have some error generator that tries to move the initial state out of the code space. And there's a competition between these two. So then let's allow the noise to act on our original code space for some arbitrary but finite time t. So both the noise and the recovery act for some finite time t. Then we apply some global decoder, ER, to do the recovery. And in fact, this global decoder can often, but not always, just be evolution under this recovery generator without the error. And then if we want our passive quantum error correction to work well, we really need to have the same feature as for active error correction. So we want some family of codes parameterized by n. Maybe it's an n by n lattice or something like that. And then as n goes to infinity, we want the probability of a logical error to occur after this entire process to fall off exponentially with n. So n will be some sort of a system size, and gamma here will be a constant independent of time for which this noise acted on. And this is really exciting. So it means that this time can be long, but as long as it's finite, we only need to do recovery once at the end. But during the evolution, this bath, this recovery generator, protects us sort of passively against the errors. And this is exciting because when you compare it to this active error correction, where you keep doing the recovery, it seems better because these recoveries are hard to do in practice. Okay, are we good, Zlatko?
Yeah, this is good. And I guess you'll maybe talk more about some of the advantages and challenges on either front and how to think about the two.
Well, yeah, we'll get to some of that. Yes. Not to all of that. Yes, some of this. Yes. Yeah, of course, this is also not free, right? Exactly. So, I mean, designing this bath will also be difficult, and it's not obvious whether it's actually more difficult to design this clever bath or to do this repeated recoveries. Yes.
Yeah, because having worked on this kind of systems for some number of years there, it's not that easy either.
I agree. Of course. Yes.
Thank you.
Okay. Yeah. So this slide you've already seen. Our overall goal will be to construct this passively protected qubit using an array of oscillators. But before I do this, I will really want to dive now into how a single oscillator can protect against one type of error. And then later, we will put them together, together with a 2D lattice into a full code. But for now, I will just dive into a single oscillator for a few slides. Okay.
And maybe one quick question on the lattice from the audience.
Yes.
So here, the boundary conditions are they open, or you've connected them on either end?
It doesn't really matter. It can be either way. So we will be using we'll be using the Ising model essentially, and so it doesn't matter as long as it takes it's this idea that I explained at the beginning. As long as to get from one logical state to another logical state, you need to break basically on the order of n bonds. You're good.
I see. So how you glue the edges together is not too material.
Yes, it doesn't matter. Mm-hmm.
Thank you.
Thanks. Yeah, but we'll talk about this, again, more when we dive into the details. So for now, I just scratched the surface of everything. Now we'll dive into the details of this oscillator, then into the details of the 2D lattice, and then I will put them together into this full model. So for now, all of this should be a little mysterious. Okay, so let's talk about this oscillator, and it's really discussed in detail in this paper, and I'm going to sort of cover this paper. So how do you do this passive correction of these photonic qubits, which I call cat qubits? I'll explain why they're called cat qubits and how this relates to symmetry breaking. So let me introduce the cat code. So consider a harmonic oscillator with the creation operator A dagger. And let's suppose that it's coherently driven with a 2-photon drive. So we create photons in pairs or annihilate photons in pairs. And let's also add 2-photon loss. So in other words, we assume we have a Lindbladian with this Hamiltonian H, the 2-photon drive, and also 2-photon loss L2, where L2 is a jump operator that removes 2 photons with rate kappa 2. So now we can do some mathematical manipulations and realize that actually this Hamiltonian plus this jump operator is actually equivalent to a single jump operator, which is very similar to this original one, except with a shift, a squared minus alpha squared, where this alpha depends on both kappa 2 and this lambda. So you can check this for yourself. But the important point now about this new jump operator is that it's easy to check the following. So let plus and minus alpha be coherent states with amplitude alpha and minus alpha. And you can immediately see that this jump operator it actually annihilates those two states. So if we start in some superposition of these two states, nothing will happen to it under the evolution under this L0. So actually, these plus and minus alpha states span the steady state manifold of this L0 Lindbladian. So it's a qubit spanned by these two coherent states. And we can call it a cat code because if this alpha is large, and then the superposition of these two coherent states is a cat state. Now let's define the symmetric and anti-symmetric cats. So alpha plus minus alpha and alpha minus minus alpha. And let's also define the parity operator, which is 1 for even Fock states and -1 for odd Fock states. Then you can easily check that these plus and minus, the even and odd states, are actually eigenstates of this parity operator with eigenvalues +1 and -1. And so you can also think of this cat qubit or this cat code, you can also think of it as a parity qubit. Because these two parity eigenstates, you can think of them as the basis states. So in this discussion, we will be focusing on the regime where alpha squared, or the number of photons in this cat code, is much larger than 1, in which case these two coherent states are approximately orthogonal. So how does passive error correction work here? So this was first discussed here, but possibly even earlier. So this is our L0 generator that stabilizes the cat code. So let's prepare a state rho 0 that is in the code space and that's stabilized by this generator. And now let's add some dephasing with a small rate kappa d. So what I mean by this is that the total evolution is now given by this stabilizing generator and also this error, where the jump operator LD is the dephasing, A dagger A. And again, we will assume thermodynamic limit for now, so that it's actually an infinite code distance. So we'll evolve now for a short time under both of these things together. Then we turn off the dephasing and let the system relax to the steady state of L0. And what this paper found is that actually you perfectly recover rho 0, assuming alpha squared is infinite. So despite the fact that you evolved under this dephasing, you still perfectly recovered rho 0. So some of the things that we show in our paper is that you also get perfect recovery even if this dephasing is applied for a long time. In fact, even if you allow your system to reach the steady state of this combined generator, you can still perfectly recover it, provided kappa d is sufficiently small. We also understood better what the dynamics is during this entire process. So, and the dynamics is that basically you have a 2x2 matrix describing your parity qubit, and then you have everything else. And this thing actually never changes, while this guy does. And this construction is called a noiseless subsystem. And this M of t, it starts in a pure state and ends in a pure state, but during this evolution under the dephasing and during the recovery process, it is temporarily in a mixed state.
And the time scale which sets what long and short is it 1 over kappa d, or it's what?
Yeah, it depends. It depends. So there are, yeah, I mean, it's given by, it's given by the dissipative gap in the system. I think if kappa d is small, yeah, I think it is actually set by kappa d. Yes, it is set by kappa d, I think. Yes.
Mm-hmm. Mm-hmm. Yeah, so it's maybe the ratio of that to like how quickly you pin yourself back to the steady state subspace. Well,
it's really given by the dissipative gap, and actually, whether it's either kappa d or kappa 2, or maybe some combination of them depending on the relative size of them. It might be. It's actually. I think. Yeah, I think if kappa 2 is large, then it's actually kappa 2. So kappa 2 was this 2 photon loss. Mm-hmm.
Got it. Thanks.
Thanks. Right. So what we also do is we classify the errors that can be passively corrected this way. It turns out that if this dephasing is smaller than the 2-photon drive, then the error is correctable. But then if this dephasing is larger than the 2-photon drive, then it's not correctable. Furthermore, if we add some detuning to our oscillator for temporarily and then turn it back off, like in the same fashion, then if this detuning is smaller than the 2-photon drive, it's again correctable. But if it's larger than a 2-photon drive, it's not correctable. And I'll explain in the later slides, why this is taking place. For now, that's just the facts. Now, we also showed that if you introduce now single photon loss, then if the single photon loss is small, then you lose your quantum bit, but you still have a classical bit that's protected in this coherent state basis. And this was, in fact, demonstrated experimentally in this paper by Laskan. However, if you add single photon loss and the single photon loss is sufficiently large, that even this classical bit is not correctable. You lose all of your information. And I will explain, all of these results in the next few slides. So to explain all of these results, you need to define a strong and weak symmetry in open systems. And so I'll explain what this is. So this is the general form of this Lindblad master equation. And let's suppose we have some symmetry, P. Like, for example, it could be this parity symmetry that I introduced in the previous slide, but it could be some other, say, Z2 symmetry. It turns out an open,
for the audience, how we define a symmetry here, or what that means, or what's the expression?
Yes, exactly. That's exactly. That's exactly what's coming up.
Okay.
Yeah. So suppose we have a symmetry P, and it turns out in an open system it can be respected in two ways: strong or weak. So the strong symmetry means that your Hamiltonian commutes with P, and also every single jumper operator commutes with P. So in particular, if we're dealing with this parity symmetry, it would mean that H is quadratic or even in the number of creation-annihilation operators, and these LJs are also quadratic or more generally even in the creation-annihilation operators. So this is a strong symmetry. However, open systems, they can also have this weak symmetry, which means that the entire Lindbladian commutes with the symmetry, but not the individual, sort of H and LJ. So it means that if you first act on your density matrix with the symmetry, and then you apply this Lindblad generator, versus the other way around, you get the same thing. So L commutes with a super operator version of this symmetry P. Now, strong symmetry implies weak symmetry, but not the other way around. So this is a stronger condition. So now, with this understanding, let's look back at our L0 generator, which stabilizes the cat qubit. So you see here that the Hamiltonian is quadratic in ANA dagger, and also this jump operator is quadratic in ANA dagger. So it means that both H and the jump operator, they both commute with this parity symmetry. So it means that P here is a strong symmetry. Now, if you consider the dephasing or this detuning, they both preserve the strong symmetry because they're both quadratic in ANA dagger. On the other hand, if you consider single photon loss, the single photon loss violates the strong symmetry, but it preserves the weak one. So it violates the strong symmetry because it's linear in A, but it preserves the weak symmetry because in some sense, this master equation itself is still quadratic in A. So because you have L and L dagger always coming together. And that's why this condition is still satisfied. And so this difference between strong and weak symmetry will explain kind of all of these results that I mentioned in the previous slide. And I will explain this in a minute. So in particular, so let me again sort of explain what the results will be, and then I will show sort of the mathematical derivation. So in particular, in the thermodynamic limit, is there a question? Or
Yeah, I guess just to make clear, if you have both present, both dissipation channels, so you have dephasing, so your A dagger A, and you have single photon loss, because everything's linear, so you have now sort of a mixed bag of both strong and weak, right? It's not like you lose it completely.
Yes. So then it's weak. So it means that these conditions no longer hold. So whatever I will say sort of in the next few slides holds in the presence of the strong symmetry, these things are out of the window, and I'm stuck with a weak symmetry. Yeah, so the mixed bag, mixed basically means that I'm weak.
I see, mixed. And I mean, is it truly weak, or is it in some sense better than just weak?
No, it's just weak. Yeah.
All right. Thank you.
Very good questions. Thank you for the questions. Yeah. So the point of the strong and like the point of the connection between the symmetry breaking and error correction is the following. So it turns out that in the thermodynamic limit, again, when alpha squared goes to infinity, there'll be a symmetry breaking transition associated with the symmetry P. And if the symmetry is strong, there's no single photon loss. We will have strong broken phase and strong unbroken phase. And the strong broken phase will harbor a qubit in the steady state. And this is the qubit that we want to protect. And it turns out that this L0 generator is in the strong broken phase, and the qubit is in fact the cat code. And any perturbation that doesn't violate the strong symmetry and doesn't take the system out of the strong broken phase can be perfectly corrected, which was indeed the case for small dephasing or small detuning. On the other hand, if we have single photon loss, then the symmetry is weak. And then we have two phases in our phase diagram in the thermodynamic limit, a weak broken phase or a weak unbroken phase. And the weak broken phase harbors a classical bit in the steady state. And any perturbation that doesn't violate this weak symmetry and doesn't take the system out of the weak broken phase can be perfectly corrected, which is the case for sufficiently weak single photon loss. And then we can recover a classical bit. Now, to explain this a little bit better, let me first remind you how this entire kind of story works in the case of Hamiltonians. So let's consider a transverse field Ising model on a chain of qubits. And let's assume that we're in a thermodynamic limit. So this Hamiltonian has this global symmetry, which is a product of x's on all the sides. And this product of x's commutes with this Hamiltonian. That's what it means for it to be a symmetry. And because Sx squared is equal to 1, this is a Z2 symmetry. Suppose that G is much greater than J, so we essentially have only this transverse field. Then the system has a unique ground state, which is just the product of the eigenstates of the plus eigenstates of X. And here the symmetry is not broken because the ground state has the +1 symmetry of this Sx. On the other hand, if G is much less than J, then we can effectively forget about this transverse field, and we have two degenerate ground states, up, 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 and down, down, down. And Sx flips one state to the other. So this is the symmetry broken phase. Now, of course, in reality, the true eigenstates are the symmetric and anti-symmetric superpositions of these symmetry broken phases. One of them has a eigenvalue +1, and the other one has eigenvalue -1. And then the sort of important point in this many-body system is that ground state degeneracy cannot be changed unless you close the energy gap or break the symmetry, violate the symmetry. And the story is similar in open systems, where now instead of the ground state degeneracy, it is the steady state degeneracy that cannot be changed unless you close now the dissipative gap instead of the energy gap, or again, violate the symmetry. And this robust degeneracy is what is key to this passive error correction.
A quick question from the audience. Could you just clarify for us, what does the thermodynamic limit mean here? Just remind us, and why is it important for this?
Yes. Yeah. So in the previous slides, the thermodynamic limit was the number the number of photons in this cat state. It was going to infinity. In this slide, the thermodynamic limit means that this chain, the length of this chain goes to infinity. And the reason it is important is because I'm using these condensed matter theory terms here as phases, phase transition, symmetry breaking. So all of these things make sense only in the limit of large systems, in the thermodynamic limit.
Right. Not that there's a finite temperature or any of that.
No. It's just the size of the system here. And this entire thing is just about the ground states.
Excellent.
Thank you for the question.
You,
okay, good. So so now the last two slides on this cat code. So now let's suppose we have weak symmetry, and we want to study what this weak Z2 symmetry breaking does in open systems. So this is our master equation. We have this parity symmetry P that satisfies P squared equal to 1. And then our Hilbert space, because of this, is divided into two types of states. States that are that have eigenvalue +1 under this symmetry, and states that have eigenvalue -1. And now if you consider the superoperator version of this parity P, which acts now on a row from both sides, it has two types of eigenoperators. If both the bra and the ket are the same, either ++ or --, and then when we act with parity on both sides, you get the eigenvalue +1. But then if bra and the ket have opposite parity, and you act on it with a superoperator, you get -1. So there are two types of superparity eigenoperators. So weak symmetry means that the superoperator commutes with our Lindbladian. So it means the following. And so in the unbroken phase, symmetry unbroken phase, we have a unique steady state with a eigenvalue 1. And an example here is that if the Hamiltonian is turned off, and if there's a single jumper operator that is photon decay, then of course the system just goes to vacuum. And this is our unique steady state, very simple. On the other hand, in the broken phase, we pick up a second steady state with a superoperator eigenvalue -1. And then the system, the steady state harbors a classical bit. And here's one example. Let's take our cat state stabilization jump operator plus single photon loss. And let's suppose that the single photon loss is sufficiently weak. Then what you find is that your steady state is actually a mixture of the two coherent states, plus alpha and minus alpha. And then if you rewrite it in terms of these parity eigenstates, you find that it's a mixture of a +1 eigenoperator of superparity and -1 eigenoperator of the superparity. And this guy is the one that is picked up in the broken phase. So we can protect the classical bit. So on the other hand, if we have a strong symmetry, that is, if our Hamiltonian and our jumper operators all commute with the parity, then now the situation is more interesting. So we can consider a left parity operator that acts on the density matrix from the left, and the right parity operator that acts from the right. These two guys commute with each other, and they commute with the Lindbladian. And each of them can have two possible eigenvalues. So they're actually now not 2, but 4 superparity sectors, kind of a plus plus, minus minus, plus minus, and minus plus. In the unbroken phase, we have 2 steady states, one in the plus plus sector and one in the minus minus sector. We must always have those two guys because things must relax somewhere. These populations must relax somewhere. So the example here is that if we have detuning and 2 photon loss, And then the steady state is just a mixture of the 0 photon Fock state and the 1 photon Fock state. And that's also a classical bit. And the most exciting place, of course, is the case where we have the strong symmetry and the broken phase, in which case every one of these sectors picks up a steady state, and now we have 4 sectors, and this steady state now harbors a qubit. So, and this is exactly what happens with our cat state generator, where if you now take the basis of plus and minus states, any density matrix in these plus and minus states is stabilized by this generator because of this strong symmetry breaking. So, so now I'm ready to move on from cats to Ising. So, any questions on cats?
Yeah, thanks, Alexey. And folks, feel free to post questions in the chat. Kelly, thanks for clarifying your question. Maybe you'll get to this later, Alexey, but I'll bring it up now and we can always circle back on it. Yep. Coming back to the question on the thermodynamic phase and expanding into what does the thermodynamic limit translate to in terms of hardware requirements needed to benefit from passive error correction using the scheme?
Right. Yeah, excellent questions. This is actually like the probably the most important question about the entire talk. So very good. So whoever asked that. So in the case of these cat codes, the thermodynamic limit means that we want to allow for a lot of excitations in this harmonic oscillator. So our errors will be suppressed exponentially in the number of excitations, as I will say in the next slide. But still, we want this number to be large. And really, the question sort of experimentally is, how harmonic can we make an oscillator and still be able to control it and still be able to design, all of these dissipators? And really, these are still very much open questions. So for now, we just worked out the theory. And as I will say in the outlook, whether we can actually design oscillators that are sufficiently nice and clean and that can go to these sufficiently large excitation numbers, that is in fact an open question. Excellent,
thank you. And there's a little bit of confusion in the chat because my internet went down. So I'm actually having to use Kunal Sharma's laptop here. So I'm replying from Kunal's name. So that, I know that may be confusing. So thank you guys for
Hi,
thanking Kunal. And
hi, Kunal. Thank you for saving us again. Good to hear you,
Kunal. Made this possible today.
Thank you, Kunal. As you always make things possible.
All right, wonderful.
Okay. Should I move on?
Yes, thank you, Kelly, for the question. Folks, keep them coming. And Alexey, please proceed.
Right, okay. So the upshot now of this story is that, well, I discussed this strong symmetry, but in reality, we will always have single photon loss. And single photon loss violates the strong symmetry. So we have to really deal with only weak symmetry in an experiment. And in the weak symmetry, in the case of weak symmetry, we can work in this weak symmetry broken phase. That we don't have a qubit, we have a classical bit. And the classical bit is a mixture of these two coherent states, alpha and minus alpha. So now let's think of our computational basis state for the rest of the talk as being not alpha and minus alpha, but this parity qubit, so plus and minus. So plus and minus will be our kind of bit states. So then single photon loss does the following. So single photon loss acting on the coherent state, it gives you this minus alpha. So it changes the sign of this coherent state. So this corresponds actually to flipping the plus state to minus state. So in this plus minus basis, single photon loss is a bit flip. And because it's proportional to alpha here, this logical bit flip rate actually becomes more and more likely as alpha grows. So it grows as the number of photons in this oscillator, number of excitations. So single photon loss and bit flip errors are pretty bad here. On the other hand, the reason we're still interested in it is that the dephasing, which causes now phase flip errors, it is exponentially protected in the number of photons. So this dephasing flips you from alpha to minus alpha, and these alpha and minus alpha are separated by a large distance in phase space, and it's very difficult to do. And this is what this entire discussion of symmetry breaking and everything, that's what we got from it. So bit flips are now unhappy, but phase flips are happy. And so the question is, how do you fix bit flip errors? So one possibility is just to do this active repetition code, kind of like what I described, like in the very first slide. You encode a logical 0 and many physical zeros, and then you just do kind of this active error correction. But I want to do everything passively. So how can I do repetition code passively? So suppose I have a Lindbladian that prepares the thermal state of a classical 2D Ising model. So this is what I want. So this is my two-dimensional Ising model. This is my Hamiltonian, which is favors alignment of the bits. And then I want to create a Lindbladian for which the steady state is a thermal state of this Ising model. And I will explain how to do this in a second. Now, the steady state actually qualitatively changes across the phase boundary. So this 2D Ising model has a classical phase transition. And in the low temperature phase, the ground state is basically one of these two ferromagnetic states. But in the high temperature phase, the steady state is basically the identity. So the steady state here is a mixture. So how am I going to create this Lindbladian that stabilizes this thermal state? You consider an m by m lattice of spins. Then the classical Ising Hamiltonian from the previous slide, I will just rewrite it now in slightly different notation. So zxy acts on sites x and y. And so I couple kind of along the x direction or along the y direction. And then the product of x's is now a symmetry, which means it commutes with a Hamiltonian. The code space is up, 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 and down, down, down. And now I want to design local dissipators that prepare the thermal state of this Hamiltonian. So this is what this is. Yeah, go ahead.
Just to be super clear, Alexey, when in Q the product runs over, what does J run over?
Yeah, so it's J. Yeah, it's J runs over all the sites. So here sites are labeled by x and y coordinates. And you can, I should have written here probably instead of J, I should have written XY and here also XY. So J runs over all sites, but here sites are written in terms of x and y coordinates. Sorry, I mixed and matched. Sorry.
No worries. Thank you.
Yeah. So our system will have a bit flip error. That's what this bit flip is. So for now, I'm just talking about spins. So no cats now. No photons. So bit flip error just flips site x, site xy. It flips it with the x Pauli operator. And this is the error I want to correct against. And the way I'm going to correct against is using these two types of dissipators. And I will explain what this is. So what this dissipator does, it considers site xy, and it checks whether the spin on the site is anti-aligned against all four spins that are above, below, to the left, and to the right of it. And if all four bonds are unhappy, then this projector is 1, and then we flip that spin. So, we're just trying to check if all four bonds are unhappy, and if they are unhappy, we flip the spin in the middle, and all four bonds become happy. That's clearly the right thing to do. And then what this P3 does, it checks if 3 bonds are unhappy. And then if 3 bonds are unhappy, it flips the middle spin. So it makes the 1 bond that was happy unhappy, but it makes 3 bonds happy. So it's again, going down in the energy of this Ising Hamiltonian. And there's a particular relationship between these rates, which is not important. So this is what I just explained. So if all 4 bonds are unhappy, this L4 flips the middle spin and makes all 4 bonds happy. And these rates are designed to respect detail balance. And because they're designed to respect detail balance, the steady state is actually a thermal state of this Ising Hamiltonian.
Hmm. And more generally, if you had like a transverse field, then this would be a lot more complicated to do, right?
Yes. With a transverse field, it'll be much more complicated. So this is just a classical, basically, system here. And it's classical here because we assume that I have no phase flips, so I don't have a Z error here yet. It will come in the next slide. And in this case, this Q is actually a strong symmetry, like I introduced in earlier slides. And this is why it all works so nicely. Yeah, so let's assume the temperature is low, so we're in the ferromagnetic phase. We initialize in some superposition of these two code words, evolve with our full noisy Lindbladian that has this single flip error, but also the correction terms for some long but finite time. And then at the end, use global majority rule as a decoder. And then what we find is that the logical bit flip error rate scales as, it drops off exponentially as the size of our m by m lattice.
Why do I have to initialize in that particular row?
So I just want to check. Whether if I started with my quantum memory in some state that I want to recover it. So I'm building a memory.
Okay, got it.
Yeah. So if I wanted just to prepare any state in the logical space, I could just let it relax. But because I'm checking protection, I start with the initial state in the code space, then I apply some errors, and I want to check that I can recover it.
Okay, thank you.
Right. And it turns out if I now allow for phase flips, which are these Z errors, now Q becomes a weak symmetry. And now we're just left with a classical bit. And in fact, these phase flips, because there are m squared of them on every side of the lattice, the logical phase flip error scales as the total number of sites. So it's m squared. So now we get to the punchline. So the cat code protects against phase flips, but not bit flips in this, in the basis that I chose. The 2D Ising model protects against bit flips, but not phase flips. So then the idea of this photonic-Ising model is to put them together to protect against both. And now what the result will be is that the cat code, the bit flip errors are bad. They scale as n, but the phase flip errors are suppressed. In the Ising model, the phase flip errors are bad, but the bit flip errors are suppressed. And in this photonic-Ising model, you end up actually multiplying these, which is not obvious, but trust me. And then as both m and n become large, both types of errors are suppressed. And in the remaining, 3 minutes, I will actually explain what that, code is. So here's the code. So we consider an m by m lattice of photonic cavities. On each site, on each cavity, we do our usual 2-photon drive and 2-photon loss, as if we're doing cat codes. So 2-photon drive and 2-photon loss. So this is what we discussed at great length. The error processes that we want to fight against are single photon loss and dephasing. And the way we're going to fight them is we're going to introduce nearest neighbor dissipators that will drive our system to sort of an Ising-like low temperature state. So in particular, we will have two types of dissipators. This L4 dissipator considers a particular site with coordinates x, y, and then checks whether the parity qubit, so Q here is this parity operator, whether the parity of the photonic state on site xy is mismatched with the parity on all 4 neighboring sites. So kind of the parity of the site in the middle is different than the parity of all 4 sites that surround it. And if this is the case, we should definitely flip the parity of the site that we're sitting on. And this is what this annihilation operator does. And similarly, this L3 checks if 3 bonds are unhappy, and then it flips the parity if 3 bonds are unhappy, and it again increases the number of happy bonds. So exactly the same ideas for the Ising model, except now here our qubit is this parity qubit that's created by the cat code. And there's a particular relationship between these, which is not important. So this is our code space again. So now it's a parity qubit on every oscillator. And then the Ising model, this Ising type dissipators, make sure that they're kind of always aligned. And so the code space is a steady state in the absence of errors. And just very briefly, I'm almost done. So as far as the errors go, the bit flips are generated by the single photon loss. The phase flips are generated by dephasing. And then the reason why we're protected against both is that the logical bit flips are suppressed by the 2D Ising model, since it requires creating an extensive number of domain walls. We covered this many times. And on the other hand, the logical phase flips are suppressed by the cat code, because they require flipping basically this alpha state to minus alpha, and they're separated far from each other in the bosonic phase space. And so we're doing full numerical simulations at the moment just to confirm that all of this is correct. But then so far, we confirmed this under 3 approximations. Either ignore phase flips and worry about only bit flips, or the other way around, and also mean field. And all of these seem to tell us that we're correct in everything that I'm saying. So with this, let me wrap up. So I showed that coupling qubits through these nearest neighbor dissipative terms may lead to error correction, this passive error correction without measurements and feedback. There are actually no-go theorems that say you cannot get a passively or self-corrected quantum memory in 2 dimensions. Well, the way we get around these no-go theorems is that every site in our lattice is a bosonic Hilbert space that is in principle infinite. So you can think of this virtual bosonic dimension on each site as the one that breaks the no-go theorem. I explained how symmetry breaking can be useful to protect a full qubit. And for the outlook, we're interested in learning whether other systems can also host a qubit due to symmetry breaking. Is the 2D lattice the lowest dimension, or can we go lower, 1D, 0D? A crucial question, which was already asked really, is I haven't covered at all how we can design these nearest neighbor coupling dissipators in experiment. They're pretty complicated. I'm checking the parity of neighboring cavities. There are some experiments and some ideas for how to do this, but we don't know the full picture yet. And finally, I just show how to do the memory, right? But we want to do quantum computing. We want to do gates. We want to do final measurements of the system. And we want to work out fault tolerance. So none of this has been done for these photonic-Ising qubits. So with this, let me thank my collaborators. So on the first paper, these cat qubits, this was led by Simon, but also Jeremy, Ron, Rex, and Victor. And the second paper on passively protected this photonic-Ising memory in a 2D, this was Simon and Leo. And let me thank my various collaborators. And Kunal is right here. And look at this, IBM. I think there'll be more IBM soon. Thank you for your attention.
Alexey, thank you very much. And you're getting live applause here. You can't see the rest of the room that I'm in, but we can say applause from Grand Central in New York City. Folks, this is a great time to post final questions in the chat, and I'll bring these up to Alexey as we go along. Maybe just to start off with the summary slide, Alexey, on you were running these numerical simulations, so maybe it's a bit preliminary, but what are you seeing in terms of the site? Are 4 sites, sufficient to start to see some of these effects, or
no, 4 sites. You mean like a 2x2? That's not good, right? So, like if you look at the errors, let's see, maybe this, So here, we're basically considering an M by M. We want an M by M array of these guys. So I should have drawn here M by M. And then on each site, we kind of want to go up to about n photons. So I would say if it's 2x2, that's definitely not going to be enough. So 4x4, 4x4, maybe you will see something. But really, it would be much better to go even higher than 4x4.
Got it. And maybe just to clarify, is there a threshold here, or what does that look like?
Is there a threshold here? So yes, there'll be a threshold. So there'll be basically 2 thresholds. So and we don't know. I don't think we know what they are. So I discussed the cat code. So the cat code protects, in our case, so the cat code protects against phase flips, and these phase flips. Let's see. Right. So the cat code protects against phase flips, and these phase flips are generated by this dephasing A dagger A. And if you remember, kind of in the very beginning, almost, I talked about the cat code. If this kappa d is sufficiently small, then as you send the number of photons to infinity, you basically fully correct it. But if this kappa d is larger than the 2-photon drive, it doesn't work. So there'll be a threshold for this kappa d in terms of the strength of your 2-photon drive. And similarly, for the bit flips, which are protected by the 2D Ising model, there'll be sort of a similar story. So there'll be basically thresholds sort of coming together from each of these halves, and somehow they'll be married together in a way that I'm not sure we even fully understand.
I see. And have you had a chance yet to think about, in a lot of these cavity systems, typically the cavities are coupled to qubits, and one of the other, error channels comes from kind of the qubit causing phase flips on the cavity.
Yes.
I wonder how that works into the model here.
Yeah. So like, just to maybe to go to the final slide quickly, so the things that we want to do, like the crazy thing that I want to do is this, right? So we want basically a Lindblad generator that simultaneously checks, like, say for this qubit, whether the parity of this qubit is anti-aligned with all 4 of the parities around it. And then if it is, we want to annihilate a photon there. And we want to do this basically continuously. So I believe the only way really to engineer these types of terms is in fact to couple to qubits. And even if qubits are perfect, it's still, even then, it's not obvious to me how to design this, because this beast is pretty complicated. And if the qubits are imperfect, I mean, that adds even more to it. But I definitely haven't thought about it.
Okay. Yeah. Thank you. Maybe this is going, but it seems like the discussion in terms of weak and strong symmetries and how that affects that's quite general, and gives you a really nice lens to think of various continuous variable codes like the cat codes or GKP
Yes.
codes, or varieties of hexagonal codes.
Yes.
Yeah. Have you? Do you want to give us a bit of a perspective beyond cat codes, and what potentially this question of optimality in some sense?
So I mean, I think this discussion is, I mean, it's useful in the sense that it helps you understand what errors you're protected against. And which errors you're not protected against. But it's at least. So actually, I don't know what to say specifically about GKP codes in terms of the strong weak symmetry. That's a great question. I'll need to think about it. I don't know. But more generally, I mean, we will never have a situation, at least from what I understand, where all of our plausible error channels keep our symmetry strong. So there will be such processes like the single photon loss that that will break our strong symmetry, violate our strong symmetry, and make the full symmetry of the system weak. And then we have to kind of make these more complicated dances in order to protect the full qubit. So, but I don't know what specifically to say about the GKP code. Yeah, sorry.
No, that's quite useful. Yeah, yeah. I think it'll be interesting to think of the various codes in this way. I think it's really nice.
Yeah, good question. Maybe I should, after we're done, I should go back and check it out.
Awesome. Great, folks. This is a good time to clarify or add any final questions. Do you guys have anything else? I think otherwise, Alexey, maybe this is a good time to just check in with you if there were any final thoughts, words, messages you want to share with us before we go ahead and close here.
No, thank you so much for the invitation, and thank you also, Kunal, for your help. and it was a lot of fun. Thanks for the great questions. Yeah, I really enjoyed it. Thanks. Let's see. Are you guys there?
Yes.